Hello, I'm Mr. Lineweber, and this is lesson 6.1 and 6.2, Forces and Work for Science 10. So we're into chapter 6 into your workbook, which is the chapter on work and energy. So we just finished chapter 5. I'll just quickly highlight some of the key points from chapter 5. In chapter 5, there's two big ideas. One of them is uniform motion. And remember that the formula that we use for motion here is velocity or speed is equal to the change in distance or displacement through some time interval. The other big idea is non-uniform motion, or what they call accelerated motion. And the formula that we're using here is acceleration is equal to change in velocity over some time interval, and acceleration is a vector. So how this connects to lesson 6.1 on forces is that when we look at Newton's first law of motion, and there's 3 of them, we'll start with the first. They mention forces and they mention how the motion is affected. So let's take a look. An object at rest stays at rest. An object in motion stays in motion. So I'm just going to highlight that. And they're going to just describe that more completely. So to stay in motion, what does that mean? It means you're going to have the same speed and the same direction. So same speed and same direction. And then here's the big idea here. Unless acted upon by unbalanced force. So this unbalanced force is something we're going to elaborate on further. And the unbalanced force, I'm just going to underline it. This unbalanced force is what's going to cause acceleration. Now we have to unpack what that means to be unbalanced. And so when we look at the 2 diagrams below, these 2 diagrams are going to be the 2 physics principles that I established at the beginning. So the first diagram is for uniform motion, and the second diagram is for accelerated motion. So let's go through the first flowchart here. So there are 2 clauses or parts to the statement above. One that predicts behavior of stationary objects and the other that predicts behavior of moving objects. The 2 parts are summarized in the following diagram. Alright, so if forces are balanced and the object is at rest, then there will be no acceleration and the object will stay at rest. This is what's happening in the diagram to the right. The physics textbook here is just laying on a table, not moving. There's a downward force on the book that we call Fg, the force due to gravity. And force of gravity always acts down on objects. We know that everything falls down, according to Newton. But we can see that the physics textbook is not moving down. It's not accelerating down. It's not in free fall. In fact, it's at rest. So this downward force, it must be balanced. So there must be an equal and opposite force upward, which they call F normal. You don't have to worry about that in Science 10. In Physics 20, we cover it more. But all you need to realize is that this upward push on the book from the table balances the downward force and the book stays at rest. The forces on the book are balanced And an object at rest will stay at rest because there's no acceleration, there's no unbalanced force. Let's go through the next flowchart here. So it says if an object is in motion and there's no unbalanced force and the acceleration is 0, it's going to stay in motion at the same speed and direction. So I can give you an example of this. So say you had an object that's moving to the right due to some applied force. Like you could imagine a person on a dog sled. The dogs would be pulling to the right, so we call that an applied force. If there was a force of friction that was equal and opposite to the left, this dog sled would be in motion to the right due to the applied force of the dogs. But the force of friction in the snow and the gliders of the dog sled would actually make sure that there would be no change in velocity. So the dog sled would just have a constant speed because the forces left and right are balanced. Now, there is also forces up and down from the surface and the weight, but because we're considering the left and right motion, that's what I focused on. All right. Now consider this a book sliding from left to right across a tabletop. So you can see in the diagram these little motion lines. It's moving to the right. Now, sometime in the prior history of the book, it might have been given a push. And so it was set into motion sometime in the past. Or perhaps it acquired its motion by sliding down an incline, like a ramp. Whatever the case, it doesn't matter. We don't want to focus on the history of the book, but rather upon the current situation of the book, sliding to the right across a tabletop. The book is in motion at the moment. There is no one pushing it to the right. Remember, a force is not required to keep an object moving. An object in motion will stay in motion. Now, because there's friction between the book and the surface, there's actually an unbalanced force to the left. And the forces shown in this diagram are here. Up and down, the downward pull of gravity and the upward pull of the table, that's still the same thing. So this physics textbook, it's not going to be like accelerating up or down. It's at rest with respect to the up and down direction. However, horizontally, it's in motion this way because of some prior history of motion. But in this current situation, we have this force of friction that's unbalanced to the left. And so this unbalanced force is going to cause a deceleration because it's going to slow the book down to a stop. In other words, it's causing an acceleration that's going to cause the speed to slow towards 0. And so reviewing this flowchart, we see that if forces are unbalanced, there is an acceleration. Now, this acceleration is going to depend on the net force, and it's going to depend inversely on mass. So I'm just going to unpack those ideas a little bit. So the formula that is given in 6.1 is F equals ma. Technically, it's the net force. Forces are vectors because they depend on acceleration and mass. So let me just explain this formula slightly. So if we were to look at how this formula works, I'm going to isolate for acceleration. So I'm just going to divide out the mass. And so when we look at how acceleration is dependent, it depends on the force. So for example, if these dogs up here were to pull harder to the right, then this acceleration could increase. If they pull with less force, then the acceleration might cause the sled to slow down. So the force that's acting on the objects depends, the acceleration of the object depends on the force net that's being applied. Now, in Science 10, we don't actually talk about net force, and it's not technically in the curriculum. However, in 6.1, there are some practice questions on it, and so just complete those at your own discretion. Now, this second thing here says that the acceleration depends inversely on the mass. So, for example, if I want this acceleration to go up, then this mass has to go down. And inversely, if I want acceleration to go down, then the mass needs to be higher. And so this is an easy thing to think about. For example, if you're to throw, say, a basketball with all of your might, you could do a pretty good job and you could throw that basketball pretty far, and that ball will accelerate quite a lot. Now, if you throw a brick that's like quite a heavy brick, and you, with the same amount of force, you apply that force to that brick, it likely will not accelerate as much because it has more mass. And so acceleration depends on mass. And mass can be quantified in different ways in Newtonian physics. And one way to look at it is the amount of matter that an object possesses. And in physics, we'll use this word called inertia. And inertia, they go over it in your workbook. Inertia is this tendency to resist the change in motion. So for really heavy objects, like a big cruise ship, they have a lot of inertia, so it's hard to turn like a big cruise ship. But for example, a speedboat, like a tiny little speedboat, it can change its direction really quickly and change its speed really quickly because it has less mass than the big cruise ship. So when we talk about inertia, we're talking about how much mass an object has. Okay, so we were talking a little bit about the force of gravity on the previous page, and we're going to elaborate more on it. And so we'll start off with the fact that mass and weight are not the same idea. So, like I said before, mass is this internal property of an object about how much matter it has, or its tendency to resist change, its inertia. Whereas an object's weight in physics, weight, which we call Fg, the force due to gravity, this is determined by other factors like what planet are you on? Are you on Earth or are you on the moon? And so this force depends on where you are in the universe. And so mass and weight, while they're interchangeable words in everyday language, in physics you have to keep these ideas separately. Weight is the force due to gravity, and it depends on what planet you're on. In fact, on Earth, your weight actually has minuscule changes. Like if you're up on the top of a mountain or if you're at sea level, there are slight variations in your weight that you wouldn't actually notice. All right. The formula for weight is mg. Now, m is your mass, and g is the acceleration due to gravity for whatever planet you're on, and this will often be given to you. Now, just note that in most of the sections of our work, g will be used as 9.81 meters per second square. Of course, this is down, and this is on Earth. And so we will use this value in Science 10, Physics 20, and Physics 30 consistently for the acceleration due to gravity on Earth. Now, if you look at the formula that I gave at the beginning for force, F equals ma, you can see the relationship here, mass, a, g. So this g is an acceleration. So it still follows that Newton's, it's called Newton's second law, F equals ma. And it's technically, the F equals ma is technically not in the Science 10 curriculum, but it's worthwhile still working with it. All right, so when you lift an object with uniform motion, you have to exert a force on it equal to its weight. And just think about lifting a heavy object or lifting a light object. What we're going to do here is we're going to be able to calculate the amount of work that you must do to lift an object from one point to another. Work, you may remember from junior high, is a force through a distance. And so if we're talking about when the work is done against gravity, so we're talking about lifting and lifting up only, because gravity acts down. So when you want to do work against gravity, you have to lift up. So the force is the weight of the object. And remember, weight is Fg. So we're going to go something like that. So the direction of the motion must be parallel to the direction of the force. So let's unpack that a little bit. The direction of the motion must be parallel to the direction of the force. That is, the distance over which work is done against gravity must be the height that you lift the object. Okay, so in order to do work on an object, you have to move it distance. And that distance, that d value, it has to be parallel to the force. So if the force of gravity is down and we want to do work, then we can only focus on up, down and up, down and up. So we only focus in on the height that the object was lifted. If you move the object horizontally while lifting it, the horizontal motion does not contribute to the work done against gravity. Therefore, you do not include horizontal distance in your calculation. And so common situations are like if you were to lift a box up a set of stairs like this, then you would use this B value, not the length of the ramp itself. You would use this height here, and often you might have to do some Pythagorean theorem in order to solve for this in like workbook questions or something like this. And regardless of the path through which you move an object, only the vertical distance is what you consider when you're doing work against gravity. So in this section, work and energy, we'll discuss motion. The effect that work has upon the energy of an object or system of objects will be investigated. The resulting velocity and or height of the object can then be predicted from energy information. In order to understand this work-energy approach to the analysis of motion, it is important to first have a solid understanding of a few basic terms. This unit will focus on the definitions and meanings of such terms as work, mechanical energy, potential energy, kinetic energy, and power. So today's lesson, we're only going to focus in on work. So I'm going to give you a definition of work now. So when a force acts upon an object to cause a displacement, it is said that work was done on the object. So there's three key ingredients which I'm going to highlight for you. In order to do work, there must be a force, there must be a displacement, and there must be a cause. In order for a force to qualify as having done work on an object, there must be a displacement and the force must cause the displacement. So this is crucial here. There are several good examples of work that can be observed in everyday life. So let's take a look at this man pushing a box. So there is a force that's acting down on the object, right? This is that force of gravity. There is an equal and opposite force acting from the floor. That's that normal force that we talked about. And then there's this applied force by the man pushing the crate. Now, obviously, the motion of this crate is going to be to the right. So the force that we would consider that's doing work would be this force applied because it's parallel to the motion. So if this crate displaces to the right, the force acting to the right is the force that is doing the work. And then later on in the unit, what we'll realize is that work, one definition of work, is the ability to change energy of an object. So, for example, before the crate was at rest and it had no kinetic energy is the energy of motion. But once the force was applied and through a distance, then the object accelerated and there now was energy in the crate due to its motion. So other examples are a horse pulling a plow through a field, person pushing a grocery cart, student lifting a backpack, a weightlifter lifting a barbell, an Olympian launching a shot put, etc. In each case described here, there's a force exerted upon an object to cause that object to be displaced. So let's look at these examples and let's see whether or not they represent examples of work. A teacher applies a force to a wall and becomes exhausted. So, no, this would not be an example of work. The wall is not displaced. And so no work is done. A book falls off a table and free falls to the ground. So I'm going to just draw a picture for this one. Remember that we had the book had that down force, it had that up force when it was on this table. But if it falls off the table and it just falls freely, this right here, free fall, then there's no longer an up force to stop it from falling. And so here, what you can see here is an unbalanced force that acts down. Unbalanced force that acts down. And so this object will accelerate because of the unbalanced force. And it will accelerate in the direction of the unbalanced force. And so this object is going to accelerate down towards the surface of the Earth. So, is work done on the object? Yes. Work is done on the object by the force of gravity, because there is a displacement as it falls. And there is a speed change, so there are some energy transfers happening. Okay, we have a waiter carrying a tray full of meals above his head, straight across the room at constant speed. So you have your waiter, he's got the tray in his hand, and he's just walking this way at a constant speed. And so this is a more of a complex example, but is any work being done? The fact that he's moving at a constant speed means that there must be a force acting left and right. So his force to the right is balanced by some force to the left. So he's moving at a constant speed. So there's no change in energy. There's no acceleration. So there's no work being done horizontally. And then the fact that the waiter is holding that little tray, like there's a down force on the tray, there's an up force of his hand holding up the tray. And so as he moves across left and right, there's no up or down motion from the force of gravity, so there's no displacement there. So no, there's no work being done here. A rocket accelerates through space. Yes, this will be an example of work being done. So there is a force. The force, expels gases to the left if it's moving to the right. All right, so these are the formulas that you're going to be working with. So I'll just mention that work is a scalar. It's not a vector. However, work can be positive and negative to talk about like energy being added, energy being removed, but we're not going to focus on that right now. Just keep in mind that it's a scalar. And the force of gravity, all forces are vectors because they depend on accelerations, and accelerations are vectors. So to calculate the weight of a person on Earth with a mass of 64 kilograms, when we're asked to calculate weight, it's going to be Fg equals mg. And so it's going to be 64 kilograms multiplied by 9.81 meters per second square. And this will come out to, with two significant digits, 6.3 times 10 to the 2. And so what we have to talk about now is this unit, kilogram meter per second square. This unit, which is a mass times an acceleration, we're going to give capital N, which stands for Newton. So this is the unit that we're going to use for force. And it's just used because we don't want to write kilogram meter per second square all the time. So we just replace that with capital N, which stands for Newton. So forces are measured in newtons, which have the primary units or the standard units kg, m, and s. Alright, so if we're asked to calculate the mass of an object that has this weight on the surface of the moon given this g value, then all we have to do is use our formula. Solving for mass, we just have to divide out g. And the weight of an object is its number of newtons. And on the moon, because the moon is a smaller planet, its value for g is smaller. This meters per second square here in the bottom. And this will calculate our mass. And it looks like we have 4 significant digits. So let's get this. 1209 divided by 1.622. 745.4, and we know that this is in kilograms. The force required to lift a 10 kilogram chair off the ground, this is just going to be its weight. Well, sorry, I don't want to confuse you. The force is going to be the weight. So to calculate the force required to lift a 10 kilogram chair, then we just need to calculate its weight. So the weight is mg. So 10 times 98.1, that's just 98.1, and with 2 significant digits, we're looking at 98 newtons. Now, remember, force is a vector, so I'll go be careful here. So the weight of a person, let's go back to the beginning. The 6.3 times 10 to the 2 newtons, that's going to be down. The force required to lift, that would be up. So it would be equal and opposite to the force down. And so the force required to lift the 10-kilogram chair, you would have to lift that at, I'll just add this, you have to lift it at a constant velocity so that there's no acceleration and the forces are balanced, equal and opposite. So that force up, you'd have to lift at a constant velocity equal to its weight. The next one just wants us to solve for G. So all you have to do is divide out mass from the force. Oh, pardon me. It just wants mg, so that's very basic. You just multiply the two. I feel like that's a repeat question. I'll let you guys finish that one off. Two significant digits, 55 times 9.81. So maybe I'll just do a little practice on significant digits. This is what the calculator spits out, and so I want, because this one has 2 sig digs, this one has 3 sig digs, I can only do 2. So that 539, I'm going to round it up to like 540, right? But then I can only use 2 significant digits, so I got to move the decimal. So it's going to be 5.4 times 10 to the 2, and forces are in newtons. And the force of gravity is going to act down. Calculate the work. So work is Fd. So these are scalar. You don't have to worry about direction. 400 newtons. So that 400 newtons, that's the weight of the box. So the weight is actually Fg. And then the 1.2 meters off the ground, that's the height that you've lifted. So 1.2 meters. And so 400 times 1.2 is 480 Newton meters. And we have 2 significant digits. So I'm just going to go 4.8 times 10 to the 2 Newton meters. And now, just like before with forces, this Newton meter unit is kind of awkward. We don't want to always have to say Newton meter. So the unit for work and energy is going to be the joule. Okay, the joule. Okay, and the last one here, a large crane has done 2.2 times 10 to the 4 joules of work in lifting a demolition ball of vertical distance, 9.5 meters. Calculate the force exerted by the chain of the crane on the ball. So work equals Fd, and we are solving for force, so we just have to divide out distance. 2.2 times 10 to the 2, 10 to the 4 joules divided by 9.5 meters. That equals F. And remember that the joule is the Newton meter, so the meters will cancel and you'll be left in newtons. Always make sure you're in the standard units for these calculations or else you'll have issues. And so with 2 significant digits, it looks like I got this value of 2,315.8 newtons. So we can actually clean that up because it's in the thousands. We can say 2.3 kilonewtons. All right, so the last section of this lesson, it's quite a long lesson. There's 2 lessons in one, is force distance graphs. So drawing a graph of force versus position will help you visualize a different way to determine the amount of work done by a force. Analyzing the graph and following the steps below, we can see that in the first diagram, if we were to shade the area underneath a force displacement graph, and we look at the area underneath as a rectangle, so area is length times width, the length is the force, and the width is the displacement. And so we can substitute that in FD, and that means that the area under a graph is the work done. So area under an FD graph is work. And so in this example, we have a constant force that's being applied, and we can determine how much work is done by calculating the area. So the graph shows that a 10 Newton force acted on an object, causing the object to move 4 meters. The area under the force position curve is a rectangle, and so there we go. For a non-constant force, we can see here that a force is changing. The shape that we end up with now as we shade from the curve down to the x-axis is a triangle. So the formula for the area of a triangle is 1/2 base times height, with the base being 4 and the height being 8. We calculate 16 Newton meters, which is 16 joules. The work is the area, the work is the same, 16 joules. Alright, so when we're working with these types of graphs, and these three that I've given to you here, you know, 2 of them look pretty challenging because you have different shapes going on. But the third one here is quite simple. So let's start with that third one. So if we want to calculate the area, we shade underneath the graph and we get the area of a shape. This time it's a rectangle, so LW. The length is 15 newtons and the width is 12 meters. And so 15 times 12, we have 180 Newton meters, which is 180 joules. Looks like they're offering 2 sig digs, so we'll go 1.8 times 10 to the 2 joules of energy or work. So I've been saying that work and energy are similar. Basically, work is the ability to do energy, or pardon me, work is the ability to change energy. So I use them interchangeably, and we can quantify that more later in the next lesson. Staying focused on these next 2 graphs, basically what you want to do is just divide the region into 2 shapes that you can work with. So in this one we have a triangle, and here we have a rectangle. So the work that's done is equal to area 1 plus area 2. And so the first one is going to be 1/2 base times height, and the second one is going to be length times width. So we have 1/2, the base is 2 meters, and the height is 2 newtons. And for the rectangle, the base is, or I'll say the length is 2 newtons, and the width is 8 meters, right, from 2 to 10, so that's 8 meters at the constant force of 2. Simplifying this, this will be 2 plus 16, we have 18, and that's the Newton meter, so that's 18 joules, and 2 significant digits looks good there. Now for this second one, it looks like we can divide the shape into 2 triangles. And so the work will be A1 plus A2, and we shade from the graph to the x-axis, 2 shapes. And so at the 15-meter mark, something happens where the force dramatically changes in a moment of time. And so we can just calculate the total amount of work done by these separate forces by looking at this graph. And so The first, well, they're both triangles, so 1/2 base height plus 1/2 base height. Let's just make sure we plug in the right values. So the first base is 15 meters and the first height is 2 newtons. And the second base, we got to go from 15 to 40. So that's going to be 25. And the height of that triangle is 4 newtons. Okay, simplifying here, we're going to have 15 Newton meters plus 50 Newton meters. Altogether, this is going to make 65 Newton meters, or 65 joules. And I'm just going to ignore that this has one sig dig here.